A mechanism for a reaction shows the path of how we get from starting with our reactants to ending with our products and everything that shows up in between. Here's an example of the steps involved in the breakdown of ozone by chlorine radicals in the atmosphere. So, in our first step, we see that O3 reacts with monatomic chlorine, forms ClO and O2. Then, that ClO molecule that was produced reacts with another chlorine molecule, regenerates this chlorine that we used in the beginning, and produces two oxygen molecules. If we were to write the overall reaction, some things cancel out here. The chlorine that was used in the beginning is regenerated later, so it doesn't appear in the overall reaction. Similarly, the ClO that was produced is then consumed again, so it doesn't appear in the overall. So what I would see here in my overall reaction, on the left-hand side, we would have two ozone molecules. And on the right, we would have three O2 molecules. But this overall reaction doesn't tell us how something gets from the beginning to the end, actually, where the mechanism shows the steps. Um, there are terms that we'll use here. An intermediate is something that is produced by an early reaction and consumed by a later one. So, in other words, it's not there at the beginning and it's not there at the end, but it was around in the middle. So in this case, for this reaction, that would be ClO. Another term we'll see here is the term catalyst. It is used and then remade. So catalysts make reactions faster by giving it a pathway that requires less energy to begin, but it doesn't appear in the overall reaction. So in this case, chlorine is catalyzing the decomposition of ozone, but it's not overall consumed because whatever is used is regenerated later. So for this problem, or for this mechanism, Cl is an example of a catalyst. There's a term that we'll use called the molecularity of elementary steps. It's a really easy thing to do. Molecularity is how many particles are reacting. Your choices are really going to be one, two, or three, but there's terms for it. So in our first example here, we would say that this is unimolecular. We would just have one A compound, it would have to be, breaking down into something else, most likely. Our next choice would be bimolecular. We can have two different things reacting, we can have two of the same things reacting, but this requires a collision of two particles. The third type, which is known as termolecular, has three things reacting at one instant. We can have three different things, we can have two in one. Now, when you think about what this means we have the simultaneous collision of three different particles. It's easy to make two things to collide, but for me to have a third thing collide and all three of these things hit at the exact same instant in order to react is just really statistically improbable. It can happen, not very likely, and past that is even less likely. So, one of the questions that you might be asked is which type of elementary step is least likely to happen and why? And the answer would be termolecular. And the reasoning is because it requires a simultaneous collision of three particles, which is not very likely at all. And then next part will come up in the next video.